So this is Lab 1, Constant Velocity by Alexis Hernandez-Tellez. Introduction. The purpose of this lab was to observe the motion of some object that is moving at the same speed without changing direction and compare the observed versus the predicted position of the object. The model used for this lab was a glow strip simulation utilizing the momentum principle, Newton's second law, to update both velocity and position. Specifically, we applied the velocity update formula before applying the position update formula. And after comparing both the predicted data to the observed data, I learned that both data models performed extremely similarly, and there was little difference in the results. The speed, velocity, and position of the object differed insignificantly between the two. This led me to learn that under a controlled environment with constant velocity, it is easy to calculate the position and speed of a moving object. So for the computational model, as previously mentioned, we use glow strip, and the computational model utilized two equations that were derived from Newton's second law. First, the velocity update formula. This took the initial velocity plus the net force over the mass times the change in time, which represented by delta t, and that gave us the final velocity. Once we had updated the velocity, we were able to update the position, and the position was obtained by taking the initial position and adding the velocity average times delta t, which in this case was just velocity final. And lastly, the model iterated over these steps for the desired time. And here on the left-hand side, on the right-hand side, you can see both a visual model and the model in terms of graph of what was outputted by the simulation. For the experiment, the system and the surroundings. The system for the experiment was a smart card, while the surroundings included the track of the smart card and the push on smart card. The initial conditions for the model were a starting position of 0, 0, 0, which is the origin, and starting velocity of approximately 0.91 meters per second. The starting velocity was calculated using the first two data points from the observed data, and the initial conditions for the experiment were simply just placing the smart card on a track and pushing it. The recording did not begin until smart card had achieved the constant velocity. And my justification for the starting velocity is we wanted both the predicted and the observed model to start from the same place. If there was any difference in their origin, it would affect the outcome. And continue. The process. The experiment began by placing the smart card upon the track and pushing the smart card. The video recorded a small segment of the track once they had achieved the constant velocity, and afterwards, we uploaded the video to Tracker, and the position of the smart card was recorded over a period of roughly 1 second. And afterwards, this recorded time and position were put into a chart, and a computational model was used to simulate both the object and the object's position and time. And finally, the two dates were placed on one graph to compare the difference. This is the code. Here, these arrows indicate the initial position and the initial velocity that we had used. You can also see the velocity update formula and the position update formula, which we had previously discussed, so that needs no explanation. Here we have the chart that we used to indicate the change in position over time. As you can see, while there is a slight discrepancy, slight changes, they are roughly the same, and they're insignificantly different. So discussion. When I created my axis, I had intentionally had smart card beginning on the origin and moving positively in the x direction. If I had inverted the axis, the smart card would have began from the origin and moved negatively in the x direction. The speed would remain the same because speed is simply distance over time and does not account for negative or positive, but the position and velocity would have been switched negative. Now, it would be possible to say how many forces were acting on the object to produce the zero net force, because in this case we had an extremely controlled environment, and the only forces were the force of gravity, the normal force from the surface, and the push given to smart card. If it hadn't been a controlled surrounding, it would not be possible to determine how many forces acted upon the smart card. And some possible errors that could have occurred during experiment include potentially having too short of a data sample to accurately gauge the speed and position of the object. Another possible error was confirmation bias when creating the prediction model. We utilized initial velocity using data from the observed object, which could have ultimately affected the final result. And for conclusion, after performing both the comparison between the observed and predicted data, I reached a conclusion that when an object is in constant velocity without changing direction and under a controlled environment, a predicted model accurately depicts the time and position of the object. Comparing both models, the observed data had an average velocity of 0.476 meters per second, while the predicted model had an average velocity of 0.480 meters per second. Overall, while the average velocity of the predicted data was slightly higher, the difference is negligible. Also, the displacement of the predicted data was slightly greater. And when creating the model, we made some assumptions, including that the net force was 0 and that the beginning position was at the origin. I also used a starting velocity that was extrapolated from the observed data as previously discussed. But overall, I think it's safe to conclude that under a controlled environment, an object in constant velocity can be accurately gauged and predicted. Thank you.